So welcome to all of you. In the last two videos we had seen nucleophilicity versus basicity, and we closed the previous video by discussing nucleophilicity and basicity down the group in polar protic solvent. So now we will extend, we will go further. Consider fluoride ion, chloride and bromide and iodide, and instead of protic solvent, now if they are present in polar aprotic solvent. What are polar aprotic solvents? Like dimethyl sulfoxide, dimethyl formamide and acetone. These are few examples of polar aprotic solvent. So before we proceed further, these polar aprotic solvents, they have some demerit. They have one problem. They cannot solvate. They cannot solvate an ion. Means when they see fluorine in them, they don't go and surround him. Somehow they both of them repel. So he will not go to fluoride ion and protects him. He will not go to fluoride ion and surrounds him. Therefore, these solvents cannot solvate an ion. Therefore, from the periodic table, down the group size increases. Therefore, the size of the fluoride ion comparatively smaller than the size of the iodine. The same is the case even in polar aprotic solvent because of inability of the solvent to solvate. Therefore, the size of the fluoride is still smaller and size of the iodine is still larger because it cannot solvate these anions. So now this is approaching, this is attacking on the carbon, and this is also attacking on the carbon. Because of the smaller size of the solvated ion, it can attack easily. Because the smallest anion can approach easily. Whereas you have iodine, because of this bulky nature, because of this larger size, so it attacks carbon with difficulty. Therefore, in polar aprotic solvent, fluoride ion is best nucleophile and iodide ion is worst nucleophile. I hope this aspect is clear. Basicity remains the same. Basicity is not affected by the size. That is the first point we had seen already in the first video. So basicity is unaffected by the size. Only nucleophilicity is affected by the size. Therefore, because of the smallest size of the fluoride ion, he keeps the electron density easily in the pocket of carbon. Because of the larger size, he cannot keep the electron density in the pocket of carbon. So this is the summary of nucleophilicity down the group. So if we take up the summary of the whole discussion, in a group, polar protic solvent. Suppose if we consider fluoride, chloride, bromide and iodine in polar protic solvent. In polar protic solvent, I minus is best nucleophile and I minus is weak. Let us take F minus is best base. Similarly, in polar aprotic solvent, F minus is best nucleophile and F minus is best base. So this is the summary of the whole discussion. Here I minus is the best nucleophile because of the solvation effect of polar protic solvent, whereas here F minus is the best nucleophile because inability of the solvent to solvate these anions. Therefore, this is the most important concept of basicity. I hope this aspect is clear. Now quickly and fastly see few more. Suppose if they give you methoxide ion, hydroxide ion, phenoxide ion and acetate ion. When all of these ions are given to you, and first you have to, when different species has the same donor atom, in all of them the donor atom is nothing but oxygen. When the donor atom is same, When the donor atom is same, so what you need to remember, nucleophilicity and basicity are parallel to each other. What does that mean? The trend of the basicity, the trend of the nucleophilicity is the same. The trend of the basicity and the trend of the nucleophilicity is the same. Therefore, try to understand the basicity. I have to write its acid. Acid is going to be methyl alcohol. Acid is going to be water. Acid is going to be phenol. Acid is going to be acetic acid. So these are the acids of these bases. These are the conjugate bases and these are the acids. And from our common sense, by using just common sense, we can decide which is the strong acid. Therefore, you can easily find this is going to be strong acid, whereas the corresponding base is going to be weak. This is going to be weak acid, whereas corresponding base is going to be strong. Therefore, basicity of methoxide ion is greater and highest among all this, where the basicity of the acetate ion is the least. This is least because its acid is stronger. Then this is a stable acid. This is the stable conjugate base. This is stable because of equivalent resonating structure. This is relatively less stable than this. It has the resonance, but it is not equivalent. Whereas these two are unstable because they are not stabilized either by resonance, they are not stabilized either by conjugation. This is like they failed in both examination, neither inductive effect nor resonance stabilizing them. Therefore, when a donor atom is same, nucleophilicity and basicity are parallel to each other. This is an important trend you to remember. While deciding the basicity, what you need to do, write their acids and look at them, feel them, sincerely ask them which of them is a strong acid. So by using your common sense, you can easily find acetic acid is the strong acid, corresponding base must be stable, and this is base stable, this must be weak base. This is the second question. This is the other aspect. Now consider the third aspect of, they might have given you methoxide ion, they might have given you ethoxide ion, they might also have given you isopropoxide ion, they might also have given you CS3, CCS3, CCS3, O minus, tertiary butoxide ion. So they might also ask you which among the four is the strong base? Which among the four is the strong base? So simple. So while you decide nucleophilicity, look at the size of the anion. While you decide basicity, don't consider the size of the anion. So nucleophilicity depends on size. As size increases, nucleophilicity decreases. Whereas basicity is independent on the size. Among these four, if you open your eyes and see, you might realize this is a bulky group. Nucleophilicity depends upon the size, and size inversely proportional to nucleophile. Therefore, because of its larger size, because of its fatness, it is a fat molecule, fat ion. Because of its fatness, it is a bad nucleophile. Because of its slimness, this is going to be strong nucleophile. Size is inversely proportional to nucleophile, whereas basicity is independent upon the size. Therefore, irrespective of the size, because of 3 methyl groups on this same carbon, this carbon is already bonded to the oxygen, which has a negative charge, and all these electron densities makes this unstable. So tertiary butoxide is unstable, therefore it is a strong base. Whereas relatively methoxide is a weak base. This is a strong nucleophile because of its small size, whereas it is bad nucleophile because of its bulky size, whereas basicity is unaffected by this size. Therefore, this is going to be strong base. This is an important point. Wherever you see tertiary butoxide, your mind should start thinking in terms of elimination. Wherever you see methoxide ion, primarily and fundamentally, your mind should start thinking this might be a substitution because it is a strong nucleophile wherever you see. So this is the fourth example, I think so. So with this, the trends and everything is clear. I hope I made myself clear to all of you.